Actually one of my favorite topics in this whole class. The methods may seem a little dry or mathematical in nature, but this is really the time where we can actually get a yes or no answer for whether our models are actually fitting well, whether they're actually meaningful, whether they're telling us something. And that's not something that we necessarily had when we were talking about unsupervised learning. So you can always perform principal component analysis, but you don't know if it's meaningful necessarily. So it's hard to get these kind of binary yes or no answers for, did this work or not? But that's what we're going to be talking about today. How do we get those answers to assess model performance and do some interpretation of the models? So first I'm just going to outline what our prediction metrics actually are. How do we actually tell what assess the accuracy of our machine learning methods? And then for pretty much the rest of the time I'm going to be expanding on this idea of overfitting that came up over and over again in the last lecture. Why do we have to think about overfitting? What is it? And how do we deal with it in practice? Because overfitting is one of the two primary challenges in supervised learning. The other is underfitting. So, but overfitting is maybe more problematic because it's insidious. You don't know when it's happening necessarily. And then we're going to talk about regularization as one of the methods for dealing with overfitting, and then data partitioning, resampling as the other set of methods for dealing with overfitting. And then last, we're going to be talking about optimizing the hyperparameters of our algorithms, which are the parameters of the algorithms themselves as opposed to the parameters of the model that we fit. And then going to try to kind of summarize all the information and give some advice for best practice for machine learning in a very general sense. So hopefully after this lecture, you'll be able to take any algorithm you want and implement it and assess whether or not you've achieved a good fit and whether it will be generalizable to new data sets, so whether you've avoided overfitting. Okay, so how do we actually assess the accuracy of our model? So how do we tell how correct our models are? So we all know accuracy is just how many true predictions we have over everything. In all the discussion, we're going to be using this kind of confusion matrix where we have our predicted, no or yes. This is a classification kind of thinking. Again, so this whole slide focuses on classification kind of metrics. The metrics for continuous data, of course, are simple sum of squared distances, any kind of distance metric that we talked about before. But the metrics for classification problems are a little more unique, and that's why we're going to discuss them at greater length here. So yeah, there's simple accuracy, which is just let me see if my pointer works. That's a little weird. Okay. So I have the spotlight pointer now. So I won't use this too much. But yeah, it's just along the diagonal you have your true predictions, and along the off diagonal you have your false predictions. So the true predictions over everything is your accuracy. Why do we have to go beyond that? Well, the accuracy does not perform well when you have unbalanced class distributions. So oftentimes in our data set, we'll have like 99 control samples and one sample that was treated with our case of interest, right? Whatever disease we're interested in a large database or something, right? So if you have a model that predicts 100 falses, it's just like, okay, nothing is happening here. That's 99% accurate, right? It's not really like a good model, but accuracy would suggest that it is. So it's easy to see from that example why accuracy doesn't perform well when your classes are imbalanced. So what other metrics do we use? So these are more involved, more nuanced, but more useful in a general case. So we have the true positive rate, which is the amount of true predictions we made over how many truths there are. This is also called sensitivity or recall. So how many of the real cases did we actually pull out by our model? And because we're not taking into account false positives in this, so you can just see that it differs from the accuracy in that we're not accounting for true negative prediction or false positives, etc. So true positive rate is distinct from accuracy. And then there's another metric you may run into, which is false positive rate, which is just 1 minus this value. And then a true negative rate, which is how many of our true negatives out of all negatives we were able to pull out. And this is often called your specificity. So if you have a sensitive method or you have high recall, you were able to recall all the true cases. If you have a high specificity, then you did not actually make too many wrong predictions. You were able to actually tell that something is negative when it is. And then against there's false negative rate also. Another useful metric is the Matthews correlation coefficient. It's a little bit involved to calculate, but it's essentially a correlation that goes between -1 and 1. And what's nice about the Matthews correlation coefficient is also good at handling imbalanced data. So if you have a very minor class, you can still use your Matthews correlation coefficient. It's essentially a ranking correlation, and it performs well, whereas something like a Pearson correlation would not.
So you can see Matthews correlation coefficient used oftentimes instead of accuracy.
Mm-hmm.
What are the benefits of one over the other?
Right, exactly this case. So in the cases of class imbalance, then Matthews correlation coefficient performs well. Like if you think of a Pearson correlation between 0 and 1, it might not perform well in cases where you have a very minor class. So there's more involved statistics behind the Matthews correlation coefficient. It's probably worth going into, and you can see that it's not a simple formula. But in practice, it performs very well. So now I'm going to talk about a couple curves that you can look at to assess the performance of your model that are essentially derived from this type of table. But the way these curves are generated is that, so if you have some model, typically what it'll do, a classification model will assign a score to every sample. Right? So, like, just say the score goes from 0 to 100, but that's completely arbitrary. And it will assign a threshold where if you're above that score, you're class 1, and below that threshold, you're class 2. Right? So, the choice of that threshold, obviously, is decided by the algorithm itself. But to assess the performance of these metrics, what we can do is generate a curve like this by varying that threshold from the minimum to the maximum value and assessing the prediction at all possible thresholds. So we generate this curve of predictions by varying our threshold for what a true call is. And that's how each of these points along this curve are generated. And at each point, you calculate, in this case, the precision and the recall. So the precision, which is another metric I didn't discuss on the last slide, is your true positive over true positive and false positive. So in this case, it's how many right calls did you have over how many calls did you make, right? So it's not how many true positive or how many positives are out there. It's how many calls did you make. So when you made a call, were you right? That's the precision, and this measures the exactness of your predictions. When I make a true call, is it right? The recall then is your true positives over true positives plus false negatives. So this is true positives over everything. We already discussed this, and this measures the completeness. How many of your true calls did you actually find, right? So ideally, a couple things you can notice here is that at the extremes, you're going to have perfect precision and perfect recall. But what you would like is this curve to be as far to the upper right as possible. You'd like to be able to find the threshold that maximizes both your precision and your recall, right? That's the performance you would like. You'd like this to be as filled an area as possible when you're interpreting this type of PR curve. But we can also come up with a metric that summarizes this in terms of both the precision and recall, and that is called the F-score, F-measure, F1 score. And this is the harmonic average of your precision and recall. We're seeing the trade-off between the exactness and the completeness of our predictions. So we want to be precise when we're making a call. We don't want to make a lot of false calls, but we don't want to be so conservative that we don't capture many of the true calls. So that's what this curve is summarizing, is this trade-off between your exactness and your completeness of your predictions. Okay? So that's the first curve. We can also generate another curve in the exact same way, but showing a different metric called the receiver operating characteristic curve. And this compares the true positive rate to your false positive rate. So again, we're generating a curve of predictions by varying a threshold for a true call. And this is kind of a continuous distribution, but typically it would look more jagged. And this true positive rate and false positive rate are also called sensitivity and specificity. We already defined these on the previous slide. But the interpretation of this is different than the PR curve. So in the case of an ROC curve, what we would like is for the curve to be skewed to the upper left in this case. So the farther up and left this curve actually is, the better your predictor is. Because in this case, we want a maximal true positive rate, so as high as possible. We want a minimum false positive rate. We don't want to have a high false positive rate, obviously. And our metric here is an F1 score. We actually just directly calculate the area under the curve, typically. The area under the curve of an ROC curve is actually, okay, so first let me just say that ideally this, the area under the curve would be 1, which would mean that it fills this entire area. But an area under the curve of 0 actually is perfect anti-prediction. So a value of 0.5 actually means no predictability. So if you see your model and it goes from 0 to 1 like that, then you have a completely garbage model. If you see an inverted ROC curve, then you did something wrong in your code, and you probably have a good model and just calculated the curve wrong. But from the statistical side, the area under the curve, the AUC of the ROC curve, is tied to a couple of statistical metrics, such as the Mann-Whitney U test and the Wilcoxon-Ring sum test. So you can calculate the statistical significance of this fit also. And there is a generalized, a more detailed version of this that's called the total operating characteristic curve. I just wanted to mention it so that you're aware it's out there, where you can get even more information out of it, but it's less commonly used, so I'm not covering it here. Okay? So just to summarize, when you're trying to assess the accuracy of your classification model, you will just assemble one of these confusion matrices that show true and false predictions versus true and false classes. And you can calculate these two types of curves and summarize the performance in something like an F1 score of a PR curve or the area under the curve of an ROC curve. That's a typical kind of metric, right? And then you get the Matthews correlation coefficient. So that will tell you the baseline performance of your model. So are we done? Was that everything? Well, we still have not assessed how well our data will perform, or our model will perform on new data sets. We've only assessed how well it performed on the data that it was trained on in the first place. Okay? So now we're going to talk about generalization, which is how well it's going to perform on new data sets, and the problem of overfitting when you try to generalize your model. So in search of generalization. So what is generalization? Well, the concept here is that you can have a model that perfectly fits your data, and it can still be a bad model. Bad meaning, in this case, that it's not generalizable to new conditions. And the classical example here is that if you have endless monkeys eventually at a typewriter, eventually one of them will compose Shakespeare. That's certainly true. That doesn't mean that that monkey that did it was a good writer. So generalization or robustness is just the ability to predict equally well on new data. And of course, that's what we actually want to do when we're setting up a statistical model. We don't want to just reproduce the exact data set we got. We want to reproduce the underlying process so that we can predict in new cases, right? Another classical example here is the nonlinear regression problem. So if you just look at our data in the red dots, you can find, if you take an n-degree polynomial, of course you can fit those points exactly, right? But there's multiple solutions. If you take a very complex model, you can get a good fit, but you would not have any idea really of where the next red dot would be in this case. And kind of foreshadowing regularization, you might instead expect, rather than one of these complicated forms, we should just take a simple linear fit here, and that would end up being more predictive on new data sets. And I kept mentioning this term robust last lecture, that certain methods are more robust, and that's why we like them. And the key concept here is just that these overfit or overtrained models are not going to be robust. They're not going to be generalizable to new data sets. So that's the key problem, but we can define it more rigorously in terms of what's called the bias-variance trade-off, which is the key challenge basically in statistical learning, is to balance your bias of your model with the variance of the model. So what is the bias? The bias is the error between the true and expected value of your model. So in this case, what is our bias? It's essentially 0 because we exactly reproduced our data set, right? So we have no bias in this case. That's great. So when we have bias, we can think of it as not being due to not having the actual correct structure of the model. So we either weren't able to account for the error, or whatever is going on in the underlying system. For example, we talked last time about how linear models are not able to capture nonlinear behavior, so that creates a bias error because we didn't have the actual structure of that generated that data in the first place. And this problem is generally termed underfitting. So we did not have enough complexity in our model to capture all the structure of the data. So what is variance? Well, variance is error due to the sensitivity to small fluctuations in data. So if your model has changed a lot after a very small change to your data or a small change to your modeling algorithm, etc., then you would say that your model has high variance. And this is what we're calling overfitting, right? So going back to this example again, maybe I should have just kept this figure here. So we said that these two fits have no bias, right? Because they perfectly reproduce the data, but they have extremely high variance because what if I took out this data point, just a single one, and refit those curves? Those curves would probably be completely different, right? There's no way that they would still pass through this point by chance, right? So that means that the models had high variance. Any small perturbation created a completely different model. That obviously means that we don't really understand the model that generated the data in the first place. And you've, in this case, overfitted your model. So how do you deal with, ideally we of course want minimal bias and minimal variance. We want to capture the structure that's there, but also allow it to be a stable model that's generalizable to new cases. So how do we deal with error? So to get a smaller bias error, we use a finer grain approximation, more complex models. But the problem is that as we use more complex models, we actually get fewer data to parameterize each level. So we start to get higher variance for the estimates of those complexities that we're adding, right? We're spreading our data thin and trying to train more and more with it, so we know less about each added parameter, for example, that we've put into our model. So as you try to reduce your bias, you will inevitably increase your variance, and that's what this trade-off, where this trade-off arises from. So we're essentially just balancing overfitting against poor fitting, overfitting versus underfitting. And that's the constant struggle when we're setting up a statistical learning or a machine learning workflow, is we want to get good performance metrics, but also stability, right? So bias and variance. Another point to consider that's related to this is what's called Friedman's paradox. So I'm just going to read this long quote and then go into a little bit about what it actually is. So Friedman's paradox is the observation that variable selection methods based on testing for significant F statistics, so these summary statistics we were talking about, commonly include explanatory variables with no relationship to the response and spuriously inflate R squared when such irrelevant variables are present. Right? So what does this mean? What this essentially is saying is that when we have large data sets, you're going to, in large numbers of variables, you're inevitably going to find variables that perform well, but they're going to be spurious in a lot of cases. So given enough variables, a high statistically significant R squared will inevitably be able to be found. And if you naively just sub-select those variables, then you're going to be building a model based on spurious correlations. So careless variable selection can lead to poorly predictive models. This is also relates to what's called the model selection bias, which is that it's a bias that's introduced when selecting the best model from a large number of candidate models. And we're going to go into this later in the lecture, how variable selection prior to running a machine learning algorithm can be extremely problematic because it's essentially overfitting based on spurious correlations, spurious associations. So how do we actually deal with overfitting then? How do we deal with this bias variance trade-off? We'd like to have some control over our models being overfit, right? And we haven't really discussed any way other than that some methods are more robust than others. So there's two primary ways. One of which is called regularization. And generally, regularization will enforce a simpler model. So it restricts the complexity of your model, and it's in such a way constrains the variance that you can have. So if you reduce the complexity of your model, then you're inherently going to be reducing the variance at the cost of some bias, and that's called regularization. And the other way is through resampling and data partitioning, where we're enforcing limited data to allow overfitting testing. And in this case, this is primarily a method for assessing your variance as you're building the model, such that you don't end up with too overfit of a model. So you prevent yourself from overfitting. Okay, so the first class is regularization. What is regularization? Regularization is actually a very general concept that's kind of interesting to think about. That in a general sense, what regularization is we're trying to incorporate some additional information into our model that makes solutions more likely. What does that mean? Well, it can mean a lot of different things. So if it's likely, then what that means is it should be generalizable. It should be more like the real model that is generating our data, right? So we're trying to add in additional considerations that make our model less variable, more likely, less overfit, however you want to think about it. And so conceptually, this could be thought of as restricting our hypothesis space. So when you take a statistical model structure, whether it's linear models, support vector machines, decision trees, whatever, that's your hypothesis for how your variables relate to your output, right? You're saying somehow your variables linearly combine and create your output, right? And through parameterization, you're saying, okay, I'm going to allow all of my variables to somehow contribute to that. That's a big hypothesis space, right? So what regularization does is you're trying to say, well, no, it's not likely that everything is possible. Only a subset of these things are possible. So you've restricted your hypothesis space through restricting your parameterization space, as we'll talk about. So there's different ways we can do this. We can add penalties into our loss function, which is the objective function of the statistical learning method, on complexity. So we just prevent complex models from, or we penalize them so they're less likely to show up. If you add complexity, it better really be worth it, right? That's essentially what you're doing. Or we can take kind of our full overfit model and we can prune it. We can forcefully simplify it and remove things that aren't contributing very much to it. Or we can include what you can generally term a priori information. And this may already be triggering some flashbacks to when we were talking about Bayesian priors, right? So a priori information and priors are very closely linked. And we talked about how Bayesian methods perform very well on small data sets. These are all very related concepts. Okay, so we've already talked about this last lecture, but now we can talk about it kind of in proper context, which is regularization by reducing complexity as part of the linear regression workflow. So we talked about how simple linear regression is going to likely end up with a non-zero coefficient on basically all of your variables, some of which are going to be larger than others, but certainly it's likely that most of your variables are not actually contributing to your output. So what we'd like to do is to create a penalty on non-zero values of parameters, a penalty on complexity of our regression. And there's two types of penalties that I'm discussing here. There's certainly more types of penalties that you can create, but the most commonly discussed are called the L1 and L2 penalties. So the L1 penalty is here is just a penalty on the absolute sum of your weightings, okay? So what this does is, this is also called the lasso method or lasso regression. So you have your typical linear regression, which is here, your target data, and then your weightings on your variables, right? But you also add a penalty on the absolute sum there. And this absolute sum, the penalty, can be seen in this diamond shape here. And what's interesting about this, to think about conceptually, is if we have some kind of value that we're fitting, the intersection of this space is the best fit in how it interacts with this penalty. So if you have an equal, what you think of as kind of like an isocline, where everything along this line is an equally good solution, right? And it's like, okay, which solution should I pick? I could have, any of these weightings all give me the same goodness of fit, right? Well, this penalty will force it to choose the value here, the least weightings. In this case, it's betas, but just pretend it's w's. The least weighted parameters on your solution. And one feature of the L1 regression that makes it so interesting and valuable is what you can see here is that, and this is a generalized feature, is that at this point, which is the minimal weight that is equal fit along this line, you actually have no weighting at all on your beta 1 parameter. You only have a beta 2 parameter. And what this means is that you have actually achieved a more sparse result, a more sparse regression, because it's only using one of your two parameters there. So your L1 regression has a naturally sparsifying property. And we really like that when we're doing statistical learning in biology, because we want to look at our model and understand it, right? We want to actually figure out what it's happening and which variables are actually relating to our output variables, right? So we love a sparse solution, and that's why we really like L1 regression. That said, the caveat is that sparse, and I'll discuss this in a slide later, is that sparse models are less stable than non-sparse models, because the choice of, essentially one way to think about it is that the choice of which variable you pick has some variance to it. And if you, again, change your data a little bit, you can actually end up picking a different variable. So you might not end up with that same set of variables every time. So we get a sparse solution with L1 regularization, but it's a little bit less stable than L2, as I'll discuss here. So L2 is a standard Euclidean penalty. So you have a penalty on the square of your weightings. And again, it looks like this, where you've achieved the minimal Euclidean distance here of your weightings. Again, this is an isocline of equal fits. It could have picked any point along this curve and it had an equally good fit. but because of the penalty, it picks the one that minimizes the squared weightings. And so in this case, what this does is it kind of spreads it out so you don't have any very large values on individual weightings. Okay, so so this point is going to have a larger a larger squared error than that point will. So it prevents one value from completely dominating your fit. And whether or not you want that is certainly a judgment call. But one consideration is that the L2 penalty is smoother, so it's going to be a more stable answer. If you change your data set a little bit, you're going to end up with a more similar model. And I already talked about how there's an extension of these, or a generalization of these, called the elastic net regression. They have very different names for historical reasons. So this, so this is L2 regularization is also called ridge regression or Tikhonov regression. Elastic net just adds these two penalties, and you have to add a relative weighting on them. So you have to balance how much L1 penalty you want and how much L2 penalty you want, and you essentially do that based on performance and how much sparsity you want.
Generally, is convergence affected a lot when you add this regularization?
Is convergence? So I've never had any problems with convergence of regression. But what I will say is that these types of penalties are not just restricted to linear regression. You can add L1 and 2 penalties on any kind of loss function. And yeah, I don't know if they would affect convergence in a general sense. I can't guarantee that they wouldn't affect convergence. They certainly. So if you're minimizing a squared value like this, it requires like a local search. So you might have some properties of non-global optimality that arise. I'd be curious. I'm not sure. Okay, so L1 regularization. This is just a summary. Also called LASSO, least absolute shrinkage and selection operator. Just an overly complicated name for what I just described. It's more interpretable. But you need to make sure that equivalent variables are accounted for. So this is that stability property that I was mentioning. You can, if you change your data set a little bit, you can end up where a variable that was previously in your model has transformed to a nearby variable that's almost as good. That's what I'm calling equivalent variables here. So you have less stability, higher variance in your model. L2 is called ridge or Tikhonov regularization. And you can combine both of them in ElasticNet. Okay, so that's everything on regularization by adding this penalty to your loss function. But there's other ways we can reduce complexity. In this case, I'm discussing this in the context of trees. We already talked about this method last time. Again, now we're just talking about it kind of more properly. But the next method to reduce the complexity of our model is called early stopping. So as you might imagine, early stopping is where we don't fully train our model. What we do is we split our data into training data and validation data, which is a very typical thing we'll be doing anyways. But we train until the performance doesn't improve on our independent data set. Okay? So I'll show what I mean in a second. Boosting trees uses a different form of early stopping where we've artificially constrained the depth of our tree. So we don't allow it to improve after a couple splits. It figures out a couple good splits to learn from the data, and then we don't allow it to learn any further, right? So we've artificially limited the complexity of our model to try to reduce the variance. And through doing so, we're enforcing that each model is going to be weak. We're accepting that each model is going to have higher bias error, right, because it's not fitting well, but we've tried to limit the variance. So what does this look like in practice, this process of splitting into training and testing data? Well, what we can do is, so this is algorithm specific, how we're actually increasing the complexity. So this could be something like you iteratively increase the depth of a tree, or in a neural network, you just run it for longer and longer times, and it just keeps adding complexity to it. So you have to find some way to vary the complexity of your model, and that's going to be specific to to each algorithm. But in this case, we have our training error in blue, and then our testing error in red as we increase complexity. And this is a very typical curve. This is a conceptual curve, but it's very typical for how it actually works in practice. Is that initially, at a very low complexity model, you're not going to have a very good fit. You're not going to have very good performance. You're like, okay, I think I have bias error. I'm going to add complexity. I'm going to make my model more complex to try to get a better fit, right? Okay, so you keep adding complexity, and your training error just goes down to 0. Eventually, you have a deep neural network, and it's perfectly fit your data, and you're happy, right? Well, obviously, you've overfit that model. So, where was it right to stop? Where was the right amount of complexity? Well, fortunately, you were smart, and you figured out that you needed a testing data set, a validation data set. And you can see here you have an inflection point where you've stopped sort of getting real performance increases and you've started to overfit. So your testing error has started to go up because of the increased variance, your lack of generalizability from your overly complex model. So this is essentially a workflow that this is describing that can be applied to any machine learning method. You just have to come up with some metric to increase the complexity. And you find where you start to see an increase in the gap between your training performance and your testing performance. And that tells you what the right level of complexity was, right? And the other nice thing is that you see that both training and testing error are going down in this region, so you have actually fit something meaningful, right? So there is meaningful structure to your data, and you're able to identify this cutoff. But past that cutoff, it's likely that you're starting to overfit. Okay. You can also, so this was about restricting complexity before, along the fitting procedure, right? But also you can restrict complexity after it's fit. And again, this is a discussion is specific to trees, but can probably be applied to anything. But as with all decision tree lingo, you have to use a tree-based term. So we're pruning trees in this case. So we have tree-specific regularization, where we're removing sections of the tree that do not substantially improve performance, right? So you look at the tree after the fact, and you're like, well, this is great, but I wish it was less complex. I only want the most essential features, right? So you figure out which branches are not useful, and you prune them. And there's a couple different metrics for doing that. One is called reduced error pruning, where you replace each node with the most common leaf below it, right? So you've removed one node that you don't think is important just by replacing it with a leaf below it. And if that doesn't affect the error, right, that much by some criteria, then you do it, right? So you just maximally simplify it in kind of a greedy way like that. Another way you can do it is called cost complexity pruning, where you're removing subtrees based on complexity weighted value, right? So if it's a big tree, you penalize it more, it better be worth adding all that complexity. Essentially that's the idea behind it. So this takes into account the overall structure of the tree a little more. Through doing that, by weighting your complexity, by taking the complexity of a branch into account, it will tend to remove large branches that don't contribute little, which of course is what we want. We want a more interpretable kind of tree. So we have not really talked about neural networks, so I'll probably bring this up again next time. So in next lecture, we're going to cover deep learning methods, neural networks, etc. But in the context of regularization, there's a specific method called dropouts for neural networks, where essentially during the fitting procedure, we try to drop nodes out with a probability p during training. So if we have some kind of full neural network, you can see that after the dropout, you've achieved a much simpler network. This creates a ton of different subnetworks, but you just compare the full network. So you analyze the full network, but with nodes weighted by how frequently they're present in the dropout networks, right? So this is another way to do kind of ensemble modeling, where you've created a bunch of dropped-out networks, and if those dropout networks worked and this node was actually in them, then it must be really important, right? So it's just another way to enforce simplicity in your model and also do some variable importance along the way. Okay, so we've talked about enforcing simplicity through penalties and through force, but we can also enforce simplicity through assumptions. And we've talked in the Bayesian context about priors and how we can think about what the underlying error structure of our data is and use that to simplify our model. So prior distributions contain our initial guess of what the data should look like, right? And this prior can be thought of as this extra information, this regularization, that's going to inhibit unlikely overfit solutions from forming. So, for example, you might think that a cluster is likely going to be Gaussian looking, right? So if you look for a cluster with a Gaussian prior, then you're less likely to get a weird cluster. That's essentially the idea behind it. So informative priors, of course, are going to be more helpful in this case. But what I want to mention here is over and over I've talked about how Bayesian methods tend to be more useful when you don't have a lot of data. They're helpful for dealing with overfitting. And that's because they have this regularization built into them. This idea that if you have a semi-useful prior, you're not going to end up with a completely garbage model, more than likely. So because of this feature that they have some idea of what the underlying distribution should look like, and they can incorporate that into their model, they have like this incorporated regularization that makes them more generalizable. And in practice, that certainly seemed to be the case where Bayesian methods tend to outperform other parameterized statistical models when you have small data sets, when you're really vulnerable to overfitting. Okay, so that was regularization, and then the other way we can deal with overfitting is by subpartitioning of our data. And we've already discussed one way with early stopping, that we can subpartition our data into training and testing data sets and figure out when to stop it. But I'm going to discuss more here how we actually can split our data up, the different ways, and how the different ways are useful for assessing overfitting. So I'm going to talk about four methods here: permutation, bootstrapping, jackknifing, cross-validation. You may have encountered these terms in various contexts, statistics or machine learning. Some are more or less popular. So just to go through them one by one then. What is permutation? So permutation is just data shuffling. So if we have our sample, and with different columns and different data values, we shuffle our columns in different ways. N times, but this is obviously without replacement. So if you have a pink, green, yellow, and white, you always end up with a pink, green, yellow, and white in every column, but just in a different order. So we're sampling without replacement. And this is often used to give an idea of the expected value given an empirical data distribution. So we've talked about a couple different permutation methods already, the Jackstraw algorithm, for example. And we also use permutation a lot to assess variable importance. So if there's not a large gap between your model that's fit with the original data set and a permuted model where essentially all the associations have been destroyed by permutation, then you've almost certainly overfit your model, right? So oftentimes what we'll do to, where permutation is used a lot is in assessing variable importance. So if we want to know, we have, for example, a random forest, like we talked about last time, right? And it's composed of thousands of trees, and it's very difficult to figure out which variables are actually important because you can't just look at all those trees and understand what your model is telling you. So to assess variable importance, what we'll often do is take every variable, right, and permute it one by one. So we destroy any information there. And if our model performance drastically decreases when we lost that variable, we permuted it, then we know that that variable should be important, right? We don't just remove it because that actually changes the structure of your model itself. So we just permute it to keep that contribution, but have just destroyed any meaning to it. So permutation is very simple, but very useful for creating these kinds of null distributions that you can compare to your real model and say, okay, if I can't outperform the null, then I don't feel very good about my model, right? So jackknifing, I'm only mentioning it really for historical context because it's one of the earlier methods, but it's actually kind of superseded by bootstrapping. But jackknifing is an iterative procedure where we leave out each observation one by one. So if we have our original sample, we first leave out the pink, then we leave out the green, then we leave out the yellow, then we leave out the white, right? And we get our jackknifed ensemble of data sets, right? That are all n-1 in length. Very simple procedure. What do we do with that? Well, we retrain our model on each of these, and we estimate how much our variance and bias has changed, and that gives some idea of your variance of your model and how well it performs, for example, on predicting the pink in this case. So this predates bootstrapping, which I'll discuss next, and it's a simple deterministic implementation. You just create n data sets, and you can assess the variance and bias of your model by trying to train on all of these jackknifed samples. Very simple procedure. So this can be generalized to bootstrapping, where we're now resampling with replacement. So this is different than permutation, where we're resampling without replacement. You can see these are all bootstrapped samples now, and in this case I ended up with 2 green just by chance. In this case I ended up with my original data set again. There I ended up with 2 white, etc., so on and so forth. So these are bootstrap samples. So a typical bootstrapping workflow is we have our original data, and we have our sample statistic that we calculated from it. And we want to know, is that good or not, right? Did I overfit or not? And this could be an F1 score, area under the curve, whatever your sample statistic is, doesn't matter. So we resample our data, we bootstrap it, pretending that we don't have all of that data, and we calculate the statistic on each of these subsamples, right? And we end up with a bootstrap distribution then that one, you can assess the gap between these to assess your bias, but you can also assess the variance. You can create confidence intervals on your parameters. So we're grabbing random subsets of our original data and retraining the model, and you can create confidence intervals from these bootstrapped distributions. So if you look at certain subsamples and you end up with a very different model, then you have less confidence, right? Etc. Okay? The next method is cross-validation. So cross-validation is another resampling method that's similar to the early stopping method that I talked about earlier. And in cross-validation, it's also called rotation estimation. Do you see that name? Well, the concept here is that we're breaking it into n folds. Okay, they're called folds. So you'll see like 1-fold cross-validation, 10-fold, 5-fold. Those are the most common. Or sorry, yeah, n-fold. What we do is we use most of the data to train. At least in this case, it's 10-fold cross-validation. So we've broken it into 10 sections, right? And 9 of those sections are used to train our model. And then we test it on that last section, right? And that's the first iteration. And then we do it again, and we get another error estimate, training and testing, another error estimate, over and over and over. Okay? So we use most of the data to train and the remaining data to test. And of course, the natural question is, why did you pick this particular division? You know, what if you switched up that division? So you'll often repeat this kind of n times and get an average. So you'll repeat like 10-fold cross-validation like this, 100 times, 1,000 times, whatever, to get convergence. So you repeat it n times with different partitions and average. So yeah, tenfold cross-validation are common, as well as leave one out, where you train on everything but one. So what does this do? This gives you a very good estimate of the bias of your model, the actual performance, the generalizability of your model. So it's more focused on how good the performance of your model is than on confidence intervals, which is more what bootstrapping is about. So typically, with the machine learning paper, if you ever look at their performance metric, they'll often report something like the leave one out cross-validation error or the tenfold cross-validation error. This is the most commonly used method in practice. I will say, though, that there is some pushback where people, there are variants of bootstrapping, called one of them is called like 0.632 bootstrapping, that have been shown to be as good or better than cross-validation as well. So there is still some consideration about what's the best method. So comparing these methods, so I already mentioned that bootstrapping supersedes jackknifing. You can think of it as a very simple sampling pattern. But comparing, maybe more interesting is comparing bootstrapping and cross-validation. So with this, bootstrapping has more bias than cross-validation and less variance. What does that mean? What it means is that bootstrapping is conservative about how well your model actually works. It will think, essentially, that your model is worse than it really is at generalizing to new conditions. So for that reason, people like cross-validation because they want to report that their model is working as well as possible, right? So bootstrapping is overly conservative in a sense, or at least the base method of bootstrapping is overly conservative compared to cross-validation for estimating how well your model works, but it's really good for confidence intervals. It's really good at assessing the variance of your model. So typically, applying both in a workflow is fine. You apply bootstrapping to get confidence intervals, and apply cross-validation to assess the final accuracy, the final bias of your model. Yeah, and so cross-validation is most commonly used to assess the generalization error. Okay, is that fun? Okay, so this is not really a resampling method, but it's a really important part of every workflow that is sadly often ignored for practical reasons. And that is the lockbox. So we already talked about division into the training and validation set for early stopping and for cross-validation, and that's all well and good. But with that, you also should be creating a real lockbox test set. And what does that mean? How is that different? So you split your data actually into training, validation, and test, and you don't touch the test until the very end, and you never change anything after you've tested it. That's the point. If you change anything after you test your lockbox, then you've ruined your lockbox and you've potentially made yourself vulnerable to overfitting. And one important consideration is that when you're doing this division, you have to be aware of your class distribution. You cannot just naively leave like 5% of your data in your test set if your 5% doesn't have any of your actual, treated samples of interest, right? So you really want to be careful about biasing your sampling such that you have somewhat even distribution of your classes within each of your sets. So oftentimes you will not see a lockbox done because of lack of data. So if you only have 100 samples and your model is really not performing very well, you'll often see just cross-validation done, but you really want to be using a lockbox whenever you actually can, whenever you have enough data to actually properly assess it. Set aside some of your data, 10% or whatever, and just don't touch it until the very end, because that's the only way, as I'll discuss later, you can really be sure that you're not tailoring your workflow to get the best model performance in a way that has essentially ruined the generalizability of your model. You've gotten really good at fitting this one data set through a lot of workflow adjustments. Okay. And on that note of imbalanced data that I just mentioned there and I've mentioned before, oftentimes in biological data sets, our data is imbalanced. In a GWAS study, the people with your mutation of interest that have the phenotype of interest may be a very, very small subset of your entire population. So this presents a problem algorithmically for a lot of these methods, resampling methods, fitting methods. A lot of them are based on distributions that are not satisfied when you have rigor classes. And we already talked about how accuracy metrics are also, you have to be careful about choosing particular accuracy metrics if you have very imbalanced data. And this imbalance can either present as rare classes or outliers in continuous data. But there's methods to partition your data. Partitions, if you're naive about it, you might divide up your data such that, for example, in the case where you have only 10% positive instances and you do tenfold cross-validation, you might end up putting all of them into a single partition, something simple like that, right? But in general, it's hard to train a model to recognize your minority class. But there are methods to resample in a way that deals with that. One of which is just to insert more of the minority case, meaning you sample the minority case more heavily to actually try to distinguish between them. You can add class weightings so that if it's in the minority class, it gets added to the objective function more heavily. Or another method that I think is pretty interesting is undersampling. You actually don't use all of your majority class data, right? So in this case, if we think that it's a problem that there's 10 and 90%, maybe we just remove 80% and just fit on 10 versus 10%. We've thrown out a lot of data, so that's, it's like, why would I do that? But you can actually choose the data sets you remove. So a method that's been proposed is called pseudo-negative sampling, means that is an undersampling method where you only take the majority class points that are similar to your minority class points. What you're doing is, if you imagine that there's a cloud of your minority class and then a bigger cloud of your majority class, you take the ones that are closest to your minority class and you only look at those. So that's going to give you the most important differences. It's like these are really similar, but somehow this one's class 1 and this one's class 0. Why were those different, right? So you're really focusing on the small differences. So I think that's a really interesting kind of undersampling approach for dealing with these kind of class imbalances. And we already mentioned that you can't use metrics like accuracy. You need ranking scores like the Matthews correlation coefficient, precision, etc. Okay? So that's everything on data resampling. I have 20 minutes or so. So I'm just going to continue now with workflows and one specific aspect of workflows that will always come up when you're trying to choose the best method, choose the best parameters of your method, and that's optimizing your hyperparameters. So what is a hyperparameter? Probably no one's heard this term before, but this is a term that's used to distinguish the parameters of the algorithm itself from the parameters of the model. Okay, so what's an easy example of this? Let's think about k-means clustering, right? What's the hyperparameter of k-means? K, exactly. So the choice of k, we've already talked a lot about how you can use the elbow method and use these clustering metrics to figure out the right k, right? That's hyperparameter optimization. So you've already done this, but very typically you'll have to define this. In dbScan, you have to define a threshold for what a neighborhood is. And there's various, or in elastic net regression, you have to assign a relative weighting of your L1 and your L2 regularization terms. So hyperparameters are all over the place, and you always have this question, okay, how do I pick them, right? And if you naively pick them, let's say if you pick them to enforce best performance, right, then you're essentially overfitting. You've really well fit your exact data set, but that doesn't guarantee it's going to be generalized to a new data set. So you'd like to optimize them, but you want to do it without overfitting. So how do you optimize it? A simple way is just grid search. You'll just try values between 0 and 1, varying every 0.1. Or you can do a more sophisticated gradient-based optimization where you try one and then calculate a local derivative around that to figure out a new dimension. Obviously, this is better in cases where you have multiple hyperparameters. And then Bayesian methods can be used as well. But the key point here is not, how do you search the space, but how do you deal with the fact that if you just pick the hyperparameters that perform best on this single data set, you're inherently making yourself vulnerable to overfitting. So how do we safely optimize our hyperparameters? So one way to think about this, why this is a problem, is that if you've tried, for example, 1,000 candidate models created by different hyperparameters, that's essentially the same as a multiple comparisons problem, where you've done a ton of p-tests. Some of them are going to fit just by luck. So there are workflows that enable you to test your hyperparameters, but let's talk about first the vulnerability of overfitting them. So this is a very typical modeling workflow, where we have our data, we pre-process it, and then we do cross-validation, right? So we get training and testing, training, testing, training, testing. Great, right? So now we've assessed the bias of our model, right? And if it's good, then we're happy. So we average these, and is it good enough, right? It's like, oh, it didn't work that well. Well, I want to switch up my workflow a little bit to see if I can get a little bit better result, right? So you go back and you modify your analysis parameters, and you redo your workflow, right? And you keep doing it, and keep doing it, and keep doing it until it's like, wow, I've got a really good performance, right? But you've essentially tailored your whole thing to fit this exact data set, right? With no assessment of whether you actually have generalizability now. You've overfit your model by tailoring your workflow. So this is a problematic workflow here. And then, yeah, you publish your average accuracy at the end of the day, and it's like, okay, this is great. Okay, so that's the problem. How do we actually optimize without overfitting? We can't do it within a single training testing workflow, as I discussed on the last slide. Instead, we want to have an independent validation as well, right? And this brings us to this algorithm that's called nested cross-validation, which is just one type of approach that actually enables you to safely do this. So nested cross-validation, we're again splitting our data, just like in cross-validation, into training and testing sets. But then we split our training sets into training validation sets. Okay, so we've sub-sampled our cross-validation. And we optimize hyperparameters only in the inner loop, through grid search or whatever. And we then use these parameters in the outer loop to test, okay? So we've enabled kind of a pseudo lockbox within a cross-validation workflow. So if our errors and our hyperparameters actually end up stable, then we have a low variance model. Then we can be satisfied with our generalizability. So what does this actually look like? So we have our cross-validation workflow up here, training and testing, etc., right? So this is what we said was not good enough. So this is now in nested cross-validation, just the outer loop, okay? But where we actually perform our hyperparameter optimization is within this inner loop. So we take our training data and we split it into training and validation, right? And so within each of these, we do allow our hyperparameters to vary. Right? So we're only optimizing our hyperparameters here, and then we're testing them here. And in this sense, our cross-validation error is not going to end up being vulnerable to hyperparameter optimization. So we haven't actually cranked around that whole loop multiple times to fit our data. We've actually just done a once-through optimization and assessment of our hyperparameters. Okay?
You optimize your hyperparameters inside of each instance of your outer loop cross-validation?
Yes, so you end up with a different set of hyperparameters for each one of these, right? So you find the best hyperparameters at this stage, and then to get your final hyperparameters, you end up with basically always with cross-validation, you end up with a different model here, right? But this model that's used at this stage will be the average hyperparameters from here, from the internal stage.
And then of the different stages on the outer loop, are those all running through the inner loop independently?
Yes. Okay. Yep. Yeah, so it's like a nested for loop, yeah. Mm-hmm. Okay, so that's about a summary of the tools that we have to assess and deal with overfitting. So what is best practice then? What should you be doing in a typical workflow? And this is just my own advice, and I'm sure that this will continue to change as the field develops, hopefully. So when you have a bad model, how do you improve it? Well, this gets back to this bias variance trade-off, and how do we select the right amount of complexity for our model? So simple rule of thumb, simple way to think about it is, if you're overfitting, simplify your model, right? If you see that you have overfitting going on through any of these metrics, training, testing, error, etc., then simplify the structure of your model. Don't use deep neural networks, try linear regression, right? This could be done also by reducing your data dimensionality or reducing your model complexity, or through regularization, which does the same thing. But if your model can't fit well, then sure, try to increase your complexity, right? So if you're not really capturing, if you're not achieving high accuracy, sure, go from linear regression to random forests and see if you can capture more, if you can get higher performance metrics. And this can be done through either more variables or data types or more complicated model structure. I already mentioned this on the regularization slide, but there's this really interesting paper called Sparse Algorithms Are Not Stable, a No Free Lunch Theorem, that discusses this issue between L1 and L2 regression. And we talked about how L1 is great because we love sparsity. It enforces sparsity, and we love having interpretable models, but you're accepting high variance there. So L1 approaches are not stable in that if you change your data set a little bit, you could actually change which variables appear in your model, which you don't really like that happening if you're trying to get an interpretation that's especially generalizability, but at least interpretable. So they're sparse but not stable. But L2 approaches are stable but not sparse, right? It's because they spread out the weightings across multiple variables. So one way you can kind of deal with this to get a free lunch maybe is to try reducing your features beforehand for sparsity and then use an L2 for stability, right? So if you pre-process your data to somehow pre-select your variables, then you can run an L2 regularization because you've already enforced sparsity. So maybe that's a solution to this. Just broadly speaking, around interpretability, how do you tell which variables are actually important in your complex model? So we've talked a lot about assessing the performance of your model, but at the end of the day, you want to look at your model and interpret what it's telling you. Well, there's a couple ways. One is just looking at your weightings. We've already done that with principal component analysis. With clustering, you can look at which variables distinguish your cluster. It's the same thing with linear regression. You can look at the weightings directly. But with ensembles of models, like a lot of these methods, resampled approaches, etc., we get either a high degree of complexity of a single model or just an ensemble of models, and we want to somehow figure out which variables are important across the entire ensemble. So we mentioned with dropout, we can just look at frequency. You can do the same thing with random forests. How often does a particular variable appear in a tree, right? Because the tree, each individual tree is going to have a restricted size. It's not going to have all the variables in there. So you can just look at frequency. We also talked about permutation as a way to assess variable importance. If you resample your variables one by one, not all together, and it destroys and retrain your model on those resampled, and removing or resampling a feature destroyed the performance of your model, then it must be an important variable. So these are some methods that you can use to actually interpret your model, and it comes down to just looking at it in a sense. But you can, rank the performance and look at the highest weightings, etc. This is just one example of this. So this was a random forest that we built in our lab for predicting enzyme kinetics. So what separates a fast enzyme from a slow enzyme? And this is now the feature importance of different network features, different enzyme structure features, the inherent biochemistry of the reaction, and the assay condition. which doesn't appear. I guess it wasn't very important. And this is what a typical plot will look like. So, just by permuting the variables, you get a difference in performance of the permuted versus the base model, and you kind of just rank them in a sense. And that tells you how important different things are.
What is K apparent?
K apparent is an in vivo kinetic constant. So we know that V max is K cat times E total. So K. Mhm.
Thanks.
Okay, so how do we summarize all of this into some kind of proposed workflow? What is the best practice workflow? Well, we start out by pre-processing our data. We look for any bias and remove any outliers. Maybe some latent variable analysis to figure out if you have any batch effects, etc. Use all the tools you have to assess bias and potentially remove any outliers. And you can also do something like PCA to remove any redundant or correlated variables. These are suggestions. I'm not saying that you would do this in absolutely everything, but if you're concerned about sparsity, if you're concerned about overfitting, these types of steps to pre-reduce your variables can be helpful for that purpose. And then you train your model and you evaluate it with something like cross-validation to see how well it works, right? And you can use regularized versions of these, whatever learning model you want. That could be, pruned versions, penalties on complexity, etc. You can optimize your hyperparameters with nested cross-validation. And I don't have this on here, but you can assess the variance, the confidence intervals on your the parameters of your model with bootstrapping. And then hopefully you left a holdout or a lockbox data to assess the final performance, right? So this is kind of a summary of this whole section on unsupervised and supervised learning for how you can create a workflow to end up with, an unbiased assessment of how generalized your modeling procedure was. What does this look like in practice? This was from another study from our lab where we were, in this case, we were predicting reaction thermodynamics. And we tried a bunch of different methods. So ridge regression, lasso regression, elastic net, random forests, and then a couple different boosted trees, so extra trees and gradient boosted trees. And we had split our data into training and testing. And you can see that we have our error on the y-axis, and you can see training and testing error. And of course, testing error is higher than the training error, so that's a sane result. But what I want to emphasize here is there's a clear gap between the training and testing difference of the linear methods here, so the simpler models, and then if you go to these more complicated tree-based models, you start to see a huge difference between training and testing error. What this says to me is that we don't actually have sufficient data to train these with low variance. We're actually significantly overfitting these models, and they're probably not that good. So what we ended up choosing was one of these, I think the elastic net result here. So this is kind of typically how you would go through and use these methods to pick the right machine learning tool. And this is just the final lockbox approach. I probably should have put this earlier. But the lockbox approach, as we mentioned, is that we have our original data and we immediately take out a lockbox. We just don't touch that for eternity. And we potentially use our cross-validation workflow. And this is, for example, this is optimizing hyperparameters through a lockbox, which is, I'd probably rather do it through nested cross-validation here. But then what you report is not the accuracy of your, locally optimized model that has been really well trained on this individual data set. You report the accuracy on this lockbox that never saw this whole iterative workflow. And that's really the safe, good practice way to assess the performance of your model. I just wanted to mention briefly, this is something you'll see a lot in the literature that I'm not super happy with, and that is the prevalence of pre-selecting features. So what you'll see a lot of times is that, and this is maybe how you would even approach a workflow if you weren't set out to build a complicated model, is you might observe a single correlation or a correlation of a couple variables. And you're like, oh, that's interesting. I want to build a more complicated predictor based on these variables, right? So you construct a model based on those features that you pre-selected, and you perform cross-validation, and you're like, wow, this works really well. But because you pre-selected your variables, you've essentially already gone through that that loop of analogous to hyperparameter optimization. You've gone through a workflow bias that has created an overfitting problem in this. So how to safely pre-select variables in cases where you just want to focus on a couple of things and you still want to build a machine learning model based on it? Well, you could reduce them based on an unsupervised manner, right? So something like PCA, where you just say, okay, this is just my data in a reduced feature space to try to deal with overfitting. Or if you do this, you have to be sure that the features you selected did not include the lockbox, right? So if you took a lockbox out before you pre-selected these features, then it's at least a little bit safer. So just to summarize then, so talked about how training models while avoiding overfitting is basically the primary challenge in supervised learning. It's very simple to add complexity, to deal with underfitting. You can just throw more and more complicated tools at it. The problem generally is how do you tell if you've gone too far, if you've overfit your model and it's not going to work on a new data set? Obviously, that's critically important when you're putting this into practice in science or industry. We talked about a couple of ways to deal with this, one of which is regularized algorithms, which control overfitting by limiting the model complexity. So you're enforcing a simple model. And the other way is through data partitioning and resampling that allow us to assess overfitting and basically prevent it by knowing knowing when to stop adding complexity. And we also talked about how to safely optimize our hyperparameters because a naive workflow can very easily tailor your model to fit very well a particular data set and lose all generalizability. So we talked about nested cross-validation as a safe way to deal with that. And then we talked about how critical lockboxes are as the only safe way to really assess the generalizability of your model. But we also talked about how the choice of how you resample or how you actually extract those lockboxes is critical because of this issue of minor populations. If you do not actually have a very representative lockbox, then you're still not going to be getting a very good assessment of your generalizability. So I would say representative lockboxes are really critical. And this is my own personal note here that there are dangers when you're pre-selecting your features that it creates the same type of overfitting, that you've already chosen the features and then you quote unquote relearn them with a more complicated workflow. That's essentially just overfit your model. Okay, so that's it.